Okay, everyone. My name is Chris Stryker. I'm a statistics PhD student at the University of Washington working with Emily Fox. And I'm here today to talk about some work in progress that we're doing on developing efficient inference methods for a hierarchical Bayesian model for clustering time series. So let's go to presentation and begin. So just to start off, this section is going to be talking about clustering time series. So the idea is that we have n observed series of a certain length t. So in this toy example on the left, the series are of length 100. So we have time points at each observation. And our goal is to separate the n series I have into different clusters. So here on the right, I've separated the data on the left into three k equals 3 clusters. So the idea, the motivation for this is that I might be interested in sharing information between different time series that are in the same cluster to be able to make better predictions or to be able to make better, to smooth the data in between to have better understandings of what's going on. So a previous student of Emily's applied this model to housing price data, but we found that the inference methods in it took way too long to run. So my research is in trying to speed this up. So just to be clear, that we're not just doing regular clustering, we have to deal with the dynamics of a time series. We could also view not just the mean or the trend in the series that we're trying to cluster, but instead maybe the correlations. So this example here, we still have time series, n time series, and we're still trying to cluster into 3 groups. But now instead of it just being following the same pattern, it could be that the dynamics. So in these examples, some of the series are going up while other series are going down. So they're correlated. Okay, and we can still use that information to help. Okay, so now I'm going to talk about models for time series. So we're going to fit a statistical model to find the clustering. Here is a linear dynamical system. So my series, I'm going to model them as yi of t. So that's the observation of the ith series at time t. And I believe that it belongs to this latent AR process. So I see emissions yit, but they're coming from some unknown series to me, xit. And that xit evolves based on the previous time point. So this model is pretty classical in statistics. It's just a simple model that allows us to correlate the observations between each other. So this is one model for one series, and I have n series, and I want to somehow induce some sort of structure between them. So there are many ways we can do this. I can somehow put some regularization on the x's, or I could do it on the y's. But for our purposes in this model, we're going to look at correlating the clusters. That's why the title has correlated time series. So the evolution, I'm saying the dynamics of the latent AR process, these x's, I want to be correlated. So this epsilon Gaussian noise, which is usually assumed to just be independent, I'm now going to say has some sort of structure. The way I'm going to do this is with like a random effect model. So what happens is I'm going to believe that each time series belongs to one of k clusters, denoted by a latent variable zi, and that each cluster has a latent factor process, eta k, from 1 to t, that denotes its evolution, so that the noise in our process, epsilon it, is distributed according to some additional noise to some latent process eta. So eta is the n-shaped thing in Greek letter. The point of this is that this type of hierarchical Bayesian model creates this type of covariance matrix of our time series. So I'm assuming that if I was to sort my series 1 through n by the latent cluster assignment zi, the covariance and the error terms from each time point would follow this block diagonal structure. So I'm describing or defining the clusters that I'm trying to find to create this type of block diagonal covariance matrix. Okay. Okay. So in terms of putting this all together in the time series model, this is now the graphical thing. I used to have just the x's and the y's, which were the individual series. But now I'm introducing these k eta variables that do create dependencies between different time series. So the ultimate goal is similar to just like a mixture model. I have latent variables z1 through n, which determine which cluster my series belong to. And I also have cluster-specific parameters, or in this case, a series, eta 1 through k, that I also want to learn. The nice thing about doing a model like this is that the series are independent, conditioned on I knowing z and eta. So that allows for efficient inference. Okay. So now we're going to talk about some of the existing methods based on Gibbs sampling for doing this. And then After that, I'll talk about why those aren't exactly fast and what we can do to speed them up. And then finally, I'll show some synthetic experiments that just preliminary tests we've run. So our goal is to learn the latent cluster assignments for each series, Z, and also the latent factor processes, eta. And we could do this by looking at the posterior. So we might have a prior belief about Z and eta, but we also have the likelihood term, and our goal is to either maximize or sample from this posterior. But the issue with this is that the Z's are combinatorial. Calculating the normalizing constant or even maximizing this is very intractable because of just the amount of variables we're dealing with. So Gibbs sampling is an idea that although the joint posterior is hard to sample or maximize, if we look at the conditionals, so if I pretend that I know all the other latent cluster assignments in the series, sampling the assignment of one series by itself is easy because I'm only looking at one thing at a time. So this leads to an iterative algorithm where I start with some initial condition or some random initialization or some smart initialization of the cluster assignments and series, and then I iteratively update one at a time, drawing from these conditional distributions. So this is very similar to what you do in a mixture model. The only difference now is that we have to deal with the time series. So the time series component comes in through the likelihood function. So here I'm trying to look at the sampling distribution for the ith series cluster assignment, Zi. So if it was to equal Zi equals k, I'm conditioning on all the data that I observed, y, the other cluster assignments, which I'm assuming that I know, and the latent factors, eta. The hard part that's different than a regular mixture model is the likelihood, because now we have this time series component. But luckily, because I set up this linear dynamical system, I can actually calculate the likelihood using the Kalman smoother algorithm, which was developed for that data. You have to slightly modify it to account for the fact that you have extra information from the etas, but it's basically all the same. And the time to compute the likelihood for any individual series scales with the length of the series and the number of clusters you're considering. So the total time for just doing one sampling process is order TKN. So it's linear in all these parameters. I'm just bringing this up because I'm going to talk about other methods, and they have different scaling. So this is naive Gibbs. And one of the downsides to this is although it has fast updates, you're able to iterate quickly, it might take many iterations to converge. So a bad initialization, a bad starting place might take a long time to move because this posterior distribution I'm sampling on conditions on a lot of information. Okay, so collapsed Gibbs sampling is this idea that was introduced that instead of just sampling from the complete conditional, where I condition on both Z and eta, I can collapse out the latent factors eta to allow my sampling distribution to explore more of the space. Okay, so the idea is that I'm conditioning on less, so the steps I make on each iteration are larger, so I'm able to get out a local optima, and I'm able to get towards the true mode of the posterior faster. The downside of this is that by integrating out the latent factors eta, I introduced dependencies in my likelihood function. So previously, I assumed that if I knew eta, all my observed data y and x were independent across series. But by integrating this out, I now create these dependencies between the time series within the same cluster. Okay. So for collapsed Gibbs sampling, we are able to make better steps, but to do the calculation of the correct likelihood, we now have to run the Kalman smoother on this collection or cluster of time series all at once. And this scales cubically in the number of series in a cluster. So instead of being order TKN, it now scales with order TKN cubed, where nk is the number of series in this one particular cluster. So this leads to, we have these two existing methods. One is based on using the naive likelihood, another is based on a collapsed likelihood. The naive likelihood scales fast per iteration, but the number of iterations you need might be large. It has slow mixing time. On the other hand, the collapsed likelihood has a faster mixing time, but scales cubically in the number of size of each cluster, which is bad. So one of the questions when I come in is our contribution is, can we somehow tune this trade-off? Can we do something that's slightly better than naive Gibbs sampling, but not take as long as collapsed Gibbs sampling? And the idea we found was to look at the collapsed likelihood. That was the hard thing to compute. Can we just approximate that? So Previously, in the previous slide, I showed that you have to run the Kalman smoother to calculate this. That's the intelligent way of doing it, but you could also numerically, just analytically write it this way. You don't actually compute it with this integral because the term in red, the posterior I'm integrating over, the beliefs of eta, is actually a multivariate Gaussian of size t. So if I was to keep track of that, I'd be keeping track of something that was t by t squared. It's very bad. We can think of it as like just an abstraction here. And instead, think of if I could come up with approximations to this posterior over eta, then maybe this integral will be easy to compute. I wouldn't have to use the Kalman smoother. I might be able to do something faster. So the two methods we looked at and analyzed were one based on subsampling. The posterior of eta k depends on all the other time series in the same cluster. So if I only condition on a subset, maybe that'll help me. Because it was scaling cubically with the number of series in a cluster. If I only use a few, that might do it. The other method was based on expectation propagation ideas, which is to approximate the full multivariate Gaussian with just a diagonal Gaussian. So instead of keeping track of quadratic things, keep track of only the diagonal. Okay, so let's talk about that. So the subsampling approximation method is I'm approximating the collapsed likelihood with just this term in red, where instead of conditioning on all the series, I'm only conditioning on a subset y tilde. The way we did this is you fix a certain number of series that you want to take, so n tilde k, instead of using nk, as many as there are, and just do that. Calculate the posterior there. You modify the Kalman smoother algorithm to do this. But the main high-level idea is that we're just using a posterior conditioned on less than the full set of data. Now, if the data allows tells you a lot about eta k, you might only need a few series. So that's the reason, the intuition for why it could be good. I don't actually need to look at all the data to get a good idea of what the latent process might be for this cluster. The downside to this is that it's not clear how many series you need to use. So for this to scale well, I want to fix the size, but that doesn't allow for it to adaptively tune. And if I have the wrong initialization, things can go bad. But this was just our starting point. Okay. So something that was more intelligent, this was based on previous stuff that I know, is based on fitting a posterior approximation. So expectation propagation is this method based on the kind of variational inference framework of things, where I'm going to approximate some posterior distribution with a distribution of a simpler form. So here, the true posterior distribution of eta k given y is a multivariate Gaussian, and instead of using that, I'm going to use a diagonal. So what I do here is I replace the true likelihood functions, the probability of yj given eta k, with site approximations tj. So this, to minimize Kullback-Leibler divergence, it's a metric that determines how far apart my approximation q is from the true thing, the correct thing, which would be the posterior that the collapse likelihood uses, the line above. So basically, I slightly modified expectation propagation to handle this. Instead of minimizing the post-KL divergence between the two terms here, I actually did it to minimize the final posterior with the site. Using a diagonal Gaussian actually leads to a slight modification of the Kalman smoother for naive likelihood. The details are going to be in the paper, and I'm glazing over it a little bit here. But basically, you would just have to do an outer loop. In addition to upsampling z and eta, you have to keep track of these site approximations t to handle the expectation propagation part of stuff. And it scales linearly. It has a similar running time to naive likelihood. So I just wanted to take a step back, show you all the methods we've talked about so far. What we're interested in is iteratively updating the latent cluster assignment zi. So you start with some initialization. What we want to do is we want to find a good clustering assignment zi. The way we're going to do this is iteratively condition on the previous, holding everything else fixed, just update them one at a time. The two existing methods on one hand is the naive, which is on the left, and collapse is on the right. We basically sample zi's according to the posterior distribution of the line above, but the hard part that makes this different than regular mixture models is the fact that we have a time series likelihood. And the correct thing to do is to use the collapse likelihood, where I integrate over this posterior p of eta k given the other y's. The naive likelihood actually is very similar to this, except instead of integrating over the posterior, I just use my previous iteration's belief, what I sampled for eta k. So you use like a delta function. This expectation propagation-like method does something slightly better than the point estimate. It gives you a diagonal Gaussian, so it gives you a little bit idea of the variance of your uncertainty about theta k. And subsampling is somewhere in between, but it really depends on the number of series you use in your subsample. So this was what I was really excited about, and this is what I'm interested in taking in further, is how do we tune this trade-off between approximating this likelihood using some of these ideas, okay? Now, one thing to note is that the naive and collapsed sampling methods are MCMC methods. They have the posterior as the stationary distribution of their chain, whereas these approximate sampling, the 1, 2 in the middle, the EP and the subsample-based ones, aren't. So it's not exactly sampling from the posterior, but if our goal is just to learn a good clustering assignment, it could be okay. So I'm going to now just briefly show some experiments in synthetic data that we were just doing to see if these methods are worth even investigating further. So basically, I set up synthetic data with 300 series, 5 groups, and time length of 100. And I was interested not necessarily in sampling from the true posterior, but rather getting good cluster assignments. So I'm going to score them according to normalized variation of information. It's a metric on cluster assignments. I could have used the RAND index instead. It's not important. So this first figure shows how the runtime per iteration of sampling cluster assignments grows for various algorithms as the size of the number of series grows. As you can see, the red line is collapsed Gibbs sampling. The time it takes grows polynomially with the number of time series, whereas all the other methods grow linearly. So naive is the fastest. EP takes a little bit longer because it has to keep track of site approximations. And the subsampling methods, I fixed only subsampling 5 series, which is really small. And that's that figure. But that just tells you how it does per iteration. It doesn't tell you how well those iteration steps are. So this figure here shows the normalized variation of information. That's how good our approximation is. We want it to be close to 0. So at 0, I'm finding the true cluster assignments that I generated. So what you can see here is that on the x-axis is the running time. So we want to be down and to the left. That's where it's good. We're not very far away from the true cluster assignments, and we did it fast. Naive is the purple line. It takes many iterations to get down, but it does this very quickly because each iteration takes very little time. Collapse is red. It gets down in very few number of steps, but each number of steps takes a long time. And what we can see is, from the title of the paper, our expectation propagation-based approach converges much quicker than naive because each iteration is making better steps. But it does this much faster than collapsed. So this is what we were hoping to do, is somehow live in the best of both worlds. Okay, so this is just for fun. This is what the synthetic data looked like. This was apparently the high signal to noise ratio. To me, I can't really see if I was to collapse all these together what the clusters were, but this is because it has to do with the correlations, not necessarily like a mean trend. So there's a similar picture for low signal to noise. And the only reason I'm showing this is that subsampling does very poorly here. It's because the initialization, you might be subsampling the wrong series. So don't use the subsampling method. So in conclusion, we use this Bayesian model to set up our stuff. And these are the methods I presented that we investigated. Thank you for your attention. Appreciate being here. And, yeah.
So if you had discrete states instead of continuous states, obviously you don't really need EP in that case, but what would still be like a reasonable approximation? Because that gets really expensive to sort of do the inference over, since now you're paying quadratic time and the length of the number of states for the smoothing. So is there a good solution if you want to do discrete state, say HMMs instead of linear dynamical systems?
So the question is, if the observations Y, instead of being continuous or real valued, they were from some
not the observation, the state itself, so the latent process.
Oh, the X.
Yeah,
okay.
Exactly.
So let's see. The main thing that we're interested in, the reason why it was continuous is because the latent processes eta were, okay. I haven't thought about this yet too much. So what would be the in-between between naive and collapsed is something worth thinking about. And I'm not sure what I would do right off the top of my head. I'm happy to talk to you more about this afterwards. My intuition is The main reason why EP works well is because it throws away the quadratic terms into a diagonal. I'm not sure what the diagonal would be for some sort of hidden state Markov model.
Gotcha. Thank you.
That's a good question.
If the lengths of the sequences are quite diverse, like some really short ones, some long ones, from the same few clusters, but would that throw off the method, the clustering method, or could you normalize for that, or would that just not matter?
So one of the nice things of having this type of linear dynamical model is that what we would want to do is be able to align the time points up so that we're following the same axis. But if you have missing observations or if the lengths of the series are too short, that isn't an issue. If there is some sort of time dilation between things, like some are on t equals 1 and then some are at t equals 1.5, you might have to refine to the smallest resolution. And to deal with large data, that might not be efficient. So you might have to do modifications there. But overall, dealing with different length time series shouldn't be a problem.
Thanks.
All right. So given the time, we'll leave all the other questions offline. Thank you again for the talk. Thank you.